All right. Okay, pleasure to be here. So today I'm going to be talking about some work that we've been doing with Raphaël, Monat, and our PhD student, Pierre Goutagny, as part of the avocat project. And so avocat actually means lawyer in French, but it sounds a lot like avocado cat in English, hence the logo. So, to give you a bit of context, let's consider some computer implementation of a computational law. Think, for instance, of something that computes your taxes, that determines whether you're eligible to social benefits. So you have this program. The question is, how do you ensure, first of all, that the program itself doesn't crash? So for instance, that you're not going to have any division by zero during the execution of your program. How do you ensure that the law it implements doesn't have any inconsistencies or unhandled cases which might prevent it from being applied in some cases? And additionally, how do you ensure that the law, the code you are implementing, actually matches the legal statutes? So how do you ensure you have some equivalence between the code and the legal statutes? So these kinds of questions are things that we are used to working on in computer science, especially in program analysis and formal verification. And so a natural question for us was, is there a way to apply formal verification techniques we are used to this kind of application domains? So if you see the first two properties as some kind of safety property and the last one as some kind of functional correctness property, can you apply existing techniques and tools to this? Formal verification is quite a large field, so let's try to scope a bit more the requirements, what we expect of formal verification tools applied to the law. So the first thing is, we want tools to be expressive enough to be able to reason about the structure of the law. So what this means is you want to have some reasoning about the base case and exception structure that commonly appears in legal statutes. The second thing is the kind of tools we are developing will be used both by computer scientists that are not necessarily formal verification experts, but also, and more importantly, by lawyers. So you want to make sure that these tools do not require any expert knowledge of verification, and in particular, you would like them to be as automated as possible. And lastly, it's not enough to have a tool that says, oh yeah, your program is great. You also want the tool to generate actionable examples or counterexamples when you have an issue. Because you want, first of all, the programmer to be able to debug their code, but also lawyers to be able to go into the text, into a legal statute, and compare it with the example you're providing to determine whether the law itself is a problem or whether the program is inconsistent with respect to the law. And so, one possible solution we have been exploring, and that I'm going to talk about today, is Concolic execution. So, I'm not going to go too deep into the technical details, but to give you a glimpse of how this approach works, let me explain what Concolic execution is on a very small and simple example program. So in this program, it's doing something very basic. You just assume you have two variables, x and y. And so if x is greater than 0, you return 0. Otherwise, if y is smaller than 10, you return 1. And otherwise, you might have an error. So how would Concolic execution work here? Well, you would start with some concrete inputs. Here picked arbitrarily to be x equals 5 and y equals 5. So you would execute your program with these inputs, and while executing the program, you would collect what we call symbolic constraints, which capture the execution path that we are currently taking. So in this case, what this is saying is all the inputs that have x greater than 0 would take the same execution path. So here, on the top right, you have an execution tree which represents the possible execution path of the program we have been exploring. So once you have this, you would like to explore a different execution path, and so you would like to generate inputs taking a different path. How to do that? We're going to rely on automated constraint solvers called SMT solvers and query them with a negation of part of the path condition that led to this execution path. So in this case here, we would query the solver with a constraint not x is greater than 0, and the solver would generate some new inputs, for instance, x equals 0 and y equals 5. You would execute the program again, collect symbolic constraints again, and get a new execution path. So here, in this case, not x is greater than 0 and y is smaller than 10. And so repeating this again, you query the solver with a negation of parts of a path condition, you generate new inputs, you run your program again with these new inputs, and now suddenly you explored all the possible behaviors of the program. And so what does this give you? First of all, this gives you a set of test cases which tests all the possible execution path of a program. And second, this does it in a way that avoids redundant test cases, in the sense that you only have one test case per possible execution of a program. So this is the core idea of Concolic execution. That's something that's been pretty well studied in standard program analysis. And so in this work, we've especially been applying it to the Catala domain-specific language that some people before me already presented. So the core idea of Catala is that to match the structure of a law, it relies on some structure which implements prioritized default logic. And so the core technical part of the approach, which I'm not going to talk about too much today, was how do you concolically execute default logic? And so we provided an encoding that allows you to do that. We implemented it in a tool that's called CUTECat, and we now have a Concolic execution tool for Catala. So to make it work, we also have several heuristics, especially for the performance of the analysis, so to try to prune test cases that might be redundant, and also for usability, especially to generate inputs that are a bit more readable and a bit more usable by users of a tool. So what CUTECat allows you to do is to test different execution paths in Catala programs, and it's particularly geared towards detecting ambiguities in the program, unhandled cases, and also possible crashes, meaning, for instance, possible divisions by zero in the program. And so we've been experimenting with CUTECat on the existing Catala programs. And on most programs, most Catala programs are pretty small, so you can have answers in a few seconds. But the interesting one was the biggest Catala program up to date, which is an implementation of the French housing benefits, which totals around 20,000 lines of Catala programs. And so we could see that our tool managed to scale to this and to generate almost 200,000 test cases in close to 7 hours, which gives you a great coverage of all the possible cases for the French housing benefits. So there is just one heuristic I would like to talk about today, which is the one about doing human-readable test cases. So to give you a very toy example, let's assume that you have a part of a law that discriminates based on some income. And so this is going to be framed as saying, well, if the income of this household is strictly greater than $20,000, then do something else, do something else. And the specifics are not really important here. So if we apply our tool to this might generate these two test cases, saying, well, in one case, the income is $20,000. In the other case, the income is $20,000 and 1 cent, which indeed is strictly greater than $20,000. Now, unfortunately, if you want to redo computations by hand, that's a bit of a pain because you don't want to handle cents and rounding and all of that. So if the only thing you want is to have something greater than 20,000, you would much rather have, say, an income of 21,000 and redo your computations with something like this. So that's something that we are providing in CUTECat using a feature called soft constraints. And so the idea of soft constraints is that you can add preferences, you can add constraints when generating inputs, which are not a priority compared to the actual path condition and to the actual logical query. And so in this case, that means that if you can find an input that says doesn't have any cent, that's the one that's going to be generated. Otherwise, you're still going to get an input. It's not going to be ideal, but at least that's one input to generate this test, to execute this test case. And so the important part is right now we are especially targeting this for this kind of monetary inputs, but this is a more general framework where the specifics of which kind of test cases you want can be specified by users directly and especially by lawyers, depending on application domains. So to conclude, today I quickly presented a new Concolic execution tool for Catala called CUTECat. And so the main job of CUTECat is to generate many test cases experimenting with different execution paths in Catala, and especially aiming to detect ambiguities and unhandled cases in Catala programs. This is something that is already integrated with the Catala build system, which means if you do have a Catala program, it's super easy to just run the tool on it and try to generate test cases and find ambiguities. And so the main question I have for the audience today is, we can detect ambiguities, we can detect unhandled cases. What would be the other interesting properties that we would like to reason about and that we would like to help lawyers with? And with that, I want to thank you for your attention.
So we still have that problem, right? That the law is in text form. So, and how do we ensure equivalence?
Right. So you're meaning how do you ensure the functional correctness with a law text?
Oh yeah.
Yeah. So that's still a tricky issue. So the main idea of Catala is that by having a language that is closer to the structure of a law, you can have these peer programming sessions between lawyers and computer scientists so that you can stay as close as possible and not have a computer scientist interpreting the law. There is still a mismatch here. And the issue becomes that you don't have a logical specification, you only have a textual specification, so it's hard to reason about this. But yeah, at least the idea here is if you have something that appears to be an issue in the program itself, you can generate concrete test cases and get a lawyer and a programmer in the room together and trying to understand precisely where there is a mismatch.
I'm just improvising here, but see, so LLMs can do interpretation in the usually imperative language is better. So can we do equivalence with Catala, this DSL, and then sort of ensure correctness there? But of course, there's no confidence there.
To be sure I understand the question, are you saying can we prove equivalence between the text and the code with LLMs?
No. So I was just thinking that we can ensure equivalence between Catala and a Java program. And then LLMs would find it much easier to convert this text to Java, for instance. But again, there is still tricky. No guarantees still, right?
Yeah, I mean, I think you can. I think the main question is, would you trust the LLM's output and how would you explain the LLM's output? But, I think that's an interesting direction for sure. It's a bit unclear at the moment whether it could replace a human in the loop.
Hi, Aymeric. Thanks for the talk. I was curious about kind of the harnessing. So to do dynamic symbolic execution, you need a harness. Is that something that's automatically provided, or is that something that is like it's part of your project?
So that's one of the things we would like to explore. So basically, to do this kind of analysis, you only need one initial test case. And then once you have the initial test case, you can compute new examples by exploring different execution paths. One very interesting avenue we intend to explore is, let's take an existing system. It likely already has its existing test harness. Can you adapt it, and can you avoid redoing some of the work so that you keep the existing tests that some administrations might have? That's something that we haven't explored yet. There are some technical reasons behind it, and I'd be happy to talk to you offline about it. But yeah, that's an interesting question.
We have a discussant who is not in the room at the moment, so I'm happy to continue with the questions for now for Aymeric or for any of the presenters.
Hello? Okay. Great question. I I don't know if we noticed an issue specifically with the fact that the LLM reasons forward, because typically what we would do is we would feed in like the statute, like the whole statute, and then be like, translate this, you know, to whatever language. And you can do that in the literate programming style of Catala, of like, translate this to like Markdown with Catala blocks in between, or you could just say like translate it directly to Dagger, for instance. I don't think that's the issue. I think the issue is more like if you tell the LLM like, here's the statute, translate it to code, and then you're like, now here's some test cases, translate those to code, then you run into issues if like if it doesn't know exactly what the kind of form the test cases are going to take, right? So like this is something we ran into with Catala, where like even just as humans, we wrote it, we like translated it to Catala, and then we tried to translate the Sara like test cases, and we found that it was challenging, and so we had to go and rewrite it. And you know, because we struggle with it as humans, we'd expect LLMs would have a similar difficulty, and that was what we found. I don't know if that answers your question.
I think yeah, it answered it, although I'll probably follow up afterwards regarding what's the correct definition. Thank you.
Hello. Yeah. I think I also have a question for you, Sam, because when I looked at the Catala programming language a while back, one of the great features is that it allowed for literate programming. That is a design feature, but also the success it had, the beautiful things that it did, was Denis and his lawyer companions actually programming this out. So the magic for me was in the pair programming, in getting the same people in the same room, which of course is the theme of what I've been trying to tell in my presentation. How do you feel the LLM fits in the chemistry of pair programming or extreme programming? Are you replacing the programmer? Are you replacing the lawyer? Are you replacing both, or just playing, seeing what happens? Thank you.
Yeah, I don't think I have a super clear answer to this. Probably Rohan has a more reasoned answer to this. I think that like, you know, there could be like a dream that's like probably way too naive, which is like replace both. It doesn't. I don't think anyone in this room actually believes that's going to work, but it was kind of just like an early stage experiment. Like, I think that one thing that we like, because we don't have any law experience, like Vas or I, we weren't able to appreciate, I think, enough like a lot of the syntactic choices in Catala to make it like more amenable to the language, like the kinds of words that